All right, it's a little bit after 11. We just started. So today, well, we'll see how many students shows up because of the bad weather situation, right? Well, it's not that bad actually. It's just rain, right? Um, not something that we're not very used to in California. But so today we're going to start chapter 17, which is the last chapter that's going to be on the final. Okay. And this chapter is going to be on sound. And as I mentioned yesterday, you're going to see a lot of parallel between what we talked about in chapter 16 and chapter 17, because sound is actually just a particular type of wave, right? Specifically, it's going to be this thing called a longitudinal wave. We're going to see this demonstration once again. And we'll see who's going to be the volunteer to hold the other side of the spring. So by the end of the class today, we should be able to calculate the speed of sound, right, in different media. The one that we're usually using, listening sound in is air. So that's how you're actually able to hear my voice. There's actually a particular speed of sound. But if I was a dolphin talking underwater to other dolphins, I guess that's what they would do, right? They would actually have a different speed of sound that's actually faster. And if you were some sort of rock creature that lives in the mountain or something like that and talk to each other through rocks, right? You can actually transmit sound through rocks also. Actually, that's not the only place where you would listen to sound through solid. What people used to do is actually, if they want to hear if a train is coming, as opposed to listening to the train through in the air, you put your ear on the tracks. You can actually hear the sound of the train coming to you before you can hear it in the air, because sound travel faster through solid things compared to air. And we're going to see this comparison in a little bit when we calculate the speed of sound in different media, okay? And we're going to be able to relate them to the wavelengths and frequencies that we already talked about for, any waves in general. So here you got a little bat flying around, and those of you, in case you don't know, bat, they're basically blind, and they actually really see through echolocation. And you're going to have a little worksheet that Ethan wants to pick it up. We can pass it out later on echolocation and how we can do calculations on sound waves of bats. Okay, so let's talk about sound wave first. First section of chapter 16, we talked about two different types of waves. The first one was this thing called transverse wave, right? Where the name transverse, meaning the displacement of the object. Can I have this demo once again? Anyone wants to hold the other end of this? Anthony, you want to hold the other end? Right. I'll be over here. You want to actually just stand up here, and that way everybody can see, because it's hard to see at this angle, right? So there's two different ways I can make a wave on this little object here. I can wiggle it up and down, right? It's actually, if I wiggle it faster, I can actually make multiple waves, right? But the other way to make a wave, right, is actually by just pulling it along the direction that I'm expecting the wave to travel, right? And this will send a wave left and right also, okay? So this is a longitudinal wave, and that's what sound is actually, as opposed to a transverse wave, which we dealt with a lot with the wave on the string, okay? Sound waves are longitudinal wave because there's actually additional pressure, and this is the lowering pressure, which is actually known as rarefaction, and then additional pressure, low pressure, high pressure, low pressure, high pressure, low pressure. And this pattern, okay, is actually the wave that's actually traveling from my mouth to all your ears. And you can actually mathematically, well, graphically draw this. So let's say you have a little speaker, okay? There are some points that has a high pressure. So as I push the sound out, it creates a little high pressure wave. But then these air molecule has to come from somewhere, right? So it actually borrows it from right before and right after it. So there's a little bit of pressure here, right? By having more air molecule here, you're going to have less air molecule here. Therefore, you create a low pressure piece here, and then high pressure, low pressure, high pressure. Okay. So the way you can graphically see it is if you plot I know we didn't talk about pressure in this class, but you can just kind of think about pressure as kind of like how much air molecules are like around, okay? Where you can plot basically a difference in pressure versus, well, in this case, position. So anywhere there's a high pressure part of the sound wave, is just have a positive delta P, meaning its pressure is slightly above atmospheric pressure, okay? Anywhere that has a low pressure part, and in atmospheric / maybe even chemistry talk, right? This is called rarefaction. And it's just a weird word for having lower pressure than usual, okay? You have a change in pressure that is slightly negative, right? Meaning compared to atmospheric pressure, it's a little bit lower, okay? And just to let you guys know, atmospheric pressure, 1 atmosphere, actually you actually use that, is 101, oops, with the K, 101,000 Pascal, or this thing called Pascal is actually as a base unit of newtons per square meter. Nothing that's too important you need to know for a final or anything like that. If you need to know that, I'll just give that to you. But 1 atmospheric, so the pressure that's actually all around us is about 100,000 times 100,000 newtons per square meter. Okay, so that's kind of the scale you're talking about. Okay, when we're making sound, or when I'm making sound in this case, right? The amount of pressure you actually, the difference in pressure you actually create is only like 10 newtons per square meter. Okay, it's a very small difference. So I'm not going to be like, you know, unless I'm a big wolf or something like that, I cannot blow down doors by just talking to it, right? That's it. That's still true. The tale that people tell, right? The little pigs and the wolves. Okay, I don't even remember what the tale is actually. But anyway, so the idea is that you can plot, right? You're not plotting the position of the air molecule. You're plotting, right, the difference in pressure, high or low, high or low. Okay, and this exactly looks like the sine wave we had for wave on a string, right? There's actually another way to plot it, which is actually completely opposite of what we're using. Okay, this is this variable S. This is the displacement of air molecule. We're not going to use that for this class, but it's just to know that in case you see something like this in the future, and say, well, what the hell is this S? The idea of this S is that, right? Remember the idea of me creating a high pressure here right in front of me is that I'm borrowing a little bit of molecule from around it. Okay, so this S is actually indicating how far these molecules actually moved, okay, away from its equilibrium point, okay? And you can see that it's actually, instead of a sine wave, it's actually basically 180 degrees out of phase, which actually creates a cosine wave instead. So whenever you have high pressure, right, the molecule didn't move that much, right? You have basically no movement. When you have low pressure, right, it lines up with the part where you also have no, you have no movement, but the part where you have these graph at 0, that's where the peaks and troughs are. Okay, they're just kind of shifted relative to each other. We're not going to use the displacement of air molecule in this class. We're just going to deal with the pressure. Okay, think of this change of pressure. This peak here is kind of like the amplitude of the wave on the string. Okay, it's the same. It's used the same way. Okay, so when we're describing sound with an equation, we're going to have this change in pressure, okay, right? That's what we're plotting, okay? And then the change in pressure max, that's the amplitude, right? And then the sine of kx minus omega t plus some phase change, right? That's the typical wave equation that we're dealing with. And this factor in front, you know, it used to be a, right, for amplitude. Now it's just the maximum change in pressure, okay? Which tells you how big the pressure change could be. Okay, basically this distance here, right? Delta P max. Just think of it as like the amplitude. Okay. Okay. All the other mathematics works the same way. You have the angular velocity, which is 2 pi times the regular velocity, which is related to the period divided by sorry, 2 pi divided by the period. You also have the k, which is the same wave number we've been dealing with before, which is just 2 pi divided by the wavelength. Okay, the speed of the wave is exact. Well, the speed of the wave is also related to the wavelength times the frequency, lambda times f, right? And since in the case of sound wave moving through the air, we don't have tensions and we don't have mass density of a string anymore, right? So we're gonna have to find another way to calculate this, okay? And this is where the next section comes up. We're gonna figure out how to calculate the speed of sound, okay? Before we talk about the speed of sound, okay, this is a little video that's, this is something I think I remember when I was a kid growing up in Hong Kong, where there's a lot of storms. I don't know, there's a lot of, do you guys hear a lot of thunders and lightning in the Central Valley? Yeah, okay, you still hear, okay. Because the past 2 years, there hasn't been like there was almost no rain, right? But I think I did hear thunder last year, okay? So this is a little video about that. We're not gonna watch the whole thing, but it allows you to calculate how far lightning strikes. If I can get the sound to work. External. Hopefully this is not going to be crazy loud. Okay, we're not going to go through the science part because they actually use miles as a unit, which is actually kind of confusing because we only use SI units. But the reason that you see the flash first is because light travel at the speed of light, which is much faster than the speed of sound, right? And therefore, there's going to be a delay between when you see the flash of light and when the sound that was created by this, crack of lightning, right, actually reaches us. Okay, and apparently, it travels 1 mile every 5 seconds, right? So that's approximately the speed of sound in non-SI units. But in our case, we can actually calculate this by going back to chapter 16, where if we want to find the speed of some sort of wave, you always just consider the elastic property of a wave, then you divide by the inertia property of the wave, and you square root the whole thing. Okay, and the idea of a wave, a sound wave emanating out, right? Just imagine either a person speaking, or in this case, a tuning fork. A tuning fork is a device that allows you to produce one frequency of wave. Because when I talk, I produces like many different frequencies of wave. I can have a higher pitch, lower pitch, but a tuning fork always produces one particular frequency of sound wave, and the sound wave propagates outward away from it spherically, okay, at the speed of sound, which we'll calculate. And this also gives you a nice diagram because, right, the distance between the peaks, meaning the peaks of the change in pressure, going back up to this picture here, right? This is still the wavelength, right? So the distance between those tells you the wavelength of the sound, and how often that sound is wiggling up and down is all still the frequency, right? The same principle for any waves also apply to sound wave, because sound is just a particular type of wave, okay? We're not going to be deriving this. I think the book actually goes through and derive a lot of the stuff, but we're just going to give you the little equation that allows you to calculate how fast sound travel through a particular gas, actually, this is actually in applies to any ideal gas, meaning air is almost ideal. So we can actually use this for air. Okay, where the speed of sound is this square root. Notice that the square root is always there, right? And then this gamma is known as the adiabatic index. Anyone, do you guys see this in like the chem major in here? Do you guys ever see this in your chemistry 1 or 2 class? It's basically tells you how many degrees of freedom a particular molecule has. But if you don't know that, this is always going to be given to you. R is the gas constant. Have you guys seen the gas constant, right? 8.31, and this has some of these funky units of joules per mole per Kelvin. The temperature is going to be in Kelvin because when we're dealing with science, you always want to use an absolute scale versus, definitely don't use Fahrenheit. Celsius you can kind of deal with because you can just subtract or add 273 to it. Okay. Okay. M is the molar mass. It's more of a chemistry term. It's basically how many mole of this particular gas exists in this cubic meter. Okay. So this is these are numbers that you can just look up. Sorry, how many kilograms per mole? Okay. All right. So if we want to calculate for nitrogen molecules, okay, meaning most of the air is around us are made of nitrogen. The adiabatic index for nitrogen molecules is 1.4, and the gas constant, as I said, is 8.31. Right. Let's say we want to calculate this at 0 Celsius, basically at the freezing point. It's pretty, cold day, maybe like last night, right? Right. That's actually 273 Kelvin. Okay. If you want to convert from degrees Celsius to Kelvin, okay, you add 273. Okay. Right. That means 0 degrees Celsius is equal to 73 Kelvin. Okay. So that's always numbers you can use to convert between Celsius and Kelvin. And I would have no idea how to convert to Fahrenheit without looking it up. Okay, so we're not going to deal with Fahrenheit. Okay, but 0 degrees Celsius, I think that's like 32 Fahrenheit, so it's a low number, right? But okay, and the molar mass for air is 0.29 kilogram per mole. If you crunch all this in your calculator, you're going to find that the speed of sound for air is 331 meters per second. Okay, in this room, it's actually a little bit faster because we are not at 0 degrees Celsius, right? Right, we'll actually have a higher temperature, so we actually have a slightly higher speed of sound. Okay, just to note that. Okay. Here are some other gases. Okay, so if you have air, you have 331. If this room was filled with carbon dioxide instead, and we'll probably not be talking too much, if that's the case. It's actually slower, 259. If it's all nitrogen, it's actually also a little bit slower. But if it was filled with helium, the speed of sound actually goes up. And that's because the molar mass of helium is smaller because the molecular mass of helium is much smaller compared to air itself. And that's why whenever someone, people do this kind of trick where they swallow a bunch of the air from a helium balloon, the helium from a helium balloon, and they get the squeaky voice, right? Because the speed of sound from their mouth is actually faster, and therefore they actually produce a different frequency of sound. And we're going to see how different speeds of sound actually allows you to produce different wavelengths of sound. Okay. So in air, it's actually very handy to basically calculate what is the speed of sound at a particular temperature, since we already know what the answer is at 0 degrees Celsius or 273 Kelvin, right? So these equations are useful because, right, you already calculated the number at 0 degrees Celsius. If you put in 0 here, right, this is just square root of 1, so you get this exactly the same answer. But let's say, it's at, instead of 0 degrees Celsius, is 30 degrees Celsius. You add this, and this will be a number that is slightly bigger than 1. You take the square root of that, right, and then you multiply it, and that will give you a factor bigger. Does that make sense? Where we have this reference point of 331, for speed of sound at exactly 0 degrees Celsius. Okay. I'm going to play around with that a little bit. Okay. So sound not only travel through air, but also travel through liquid if you were a dolphin. Okay. So the speed of sound in liquid, it can be calculated through this other factor. This is known as the bulk modulus. And rho down here is the density of water or liquid, whatever liquid you're talking about. Okay. So this is the bulk modulus. Just Google these sort of stuff. You can actually find them for different liquids. This is density, okay, of the liquid. Okay. Right. As long as you plug all these numbers in SI units, okay, right? For example, for water, the bulk modulus of water is actually 2.2 times 10 to the 9 Pascal. Remember, this is like a pressure unit. And then the density of water is approximately 1,000 kilogram per cubic meter, right? You have a cubic meter of water, it's going to have a mass of about 1,000 kilograms. Okay. You plug all this number in, you're going to get about 1,500 meters per second. Notice that the speed of sound in water is much higher, right? Right. In fact, it's about 4.5 times higher than the speed of sound in air, right? So if you want to, if you know, let's say you're on two people on the ship and you want to talk to each other, it's probably faster for you to just dunk yourself in water and just talk to each other through water if you're able to do that, okay? So dolphins can actually communicate with each other faster than we can, right? Different types of liquids will have different bulk modulus and density, and these are just kind of listed here. Human is mostly made of water, so therefore the speed of sound in humans is approximately the same as water, okay? Okay. Right. For solids, okay, solid, as I said, it actually have some of the highest speed of sound in it. Instead of the bulk modulus, you have this thing called Young's modulus. Okay, it's just named after some guy named something Young. Okay, but then the denominator is also the density of that material. Okay, so as I mentioned, for if you want to hear when if the train is coming, right? The speed of sound on steel, which is mostly what train tracks are made of, is actually about 6,000 meters per second. So you can actually hear the train coming faster. Sorry, you can hear the train coming way before, right? You're able to hear it through the air because the sound that the train creates traveling through the steel rail is much faster compared to the speed of sound that's actually created when the train is going through the air, basically making the honk sound, right? So it may not be as loud, but you're going to hear it first, okay? And that's the idea for being able to calculate the speed of sound in different materials, okay? All right. And you can relate the speed, the wavelength, and the frequencies of any waves, right? By just computing, the frequency and times the wavelength is always going to be the speed of that particular sound, no matter what type of wave, right? Wave on a string, sound, electromagnetic wave, they all have the same thing. The one thing to note is that when you hear a high frequency sound, okay, right? Since in a particular medium, right? Let's say we're talking in air, right? The speed of sound is going to be about 340 meters per second. So that's a constant, right? For that particular medium, okay? If I was to produce a high frequency sound, okay, it will actually have a short wavelength, right? Because the product of these two things has to multiply to a constant, right? This is why, I don't know if people actually still have these big speakers like this, right? On like a fancy stereo system, they actually have a bigger speaker for the bass, and then they have a smaller speaker called the tweeters for the higher frequency sound, okay? So the high frequency wave have shorter wavelengths, so you can actually produce the sound with a smaller speaker, but for lower frequency wave, it actually has a longer wavelength, And therefore, you need actually a bigger speaker in order to produce that sound. Okay, and we can actually calculate the wavelengths of these things pretty easily. Okay, so let's do any questions before I do the example, and then jump into the worksheet. Okay, so the range of human hearing. So, well, I think maybe you guys can hear down to 20 hertz. That's the lowest frequency sound we can hear. The highest frequency peaks, on average, well, most people can hear is actually 20,000 kilohertz. So we have this broad range of different frequencies we can hear. If you actually want to go on YouTube, there's actually a test that allows you to test, when does your hearing stop? I think mine stops at about 15,000 kilohertz because, as you get older, you lose the ability to hear high frequency sound. Okay. What this question asks you to do is to find the wavelength of sound at the extremes of human hearing. So, we're just going to plug in either 20 hertz or 20,000 20,000 hertz. Okay. At an air temperature of 30 degrees Celsius. Okay. And they just ask you to be accurate to at least 2 sig figs. Okay. So the information we got, right, is that, well, the low frequency we got is 20 hertz. And then the other frequency, the highest frequency we can hear is 20,000 hertz, right? The other information we're given is actually just temperature in Celsius, okay? 30 degrees Celsius, okay? In fact, what I'm gonna do is I'm gonna convert this to Kelvin, right, by adding 273 to it, which was gonna come out to 303 Kelvin, okay? Just so I have both numbers around, okay? What they ask you to figure out is that, well, what is the wavelength for a low frequency sound, right? Remember that, right? And the wavelength for the high frequency sound, okay? So the solution is that, well, we know that the speed of sound, right, is always gonna be the wavelength times the frequency. So we can solve this for the wavelength in general, oops, which is gonna be the speed divided by the frequency. This we know, but we don't know what the speed of sound is, right, at this particular temperature, okay? This is where this little equation up here comes in useful, right? We can either plug it into this long, this equation up here, or we can use the kind of the semi-derived one, right? Because we're just comparing it to the speed of sound at 0 degrees Celsius. So let's use, since I already converted it to Kelvin, let's use this one, right? 331 times the square root of the temperature in Kelvin divided by 273. So let's see what that number comes out to be. Okay. So the speed of sound is square root, 331 meters per second times the square root of the temperature in Kelvin divided by 273 Kelvin. And we're at 303. So it's going to be a little bit bigger, right? Because the stuff in the square root is bigger than 1. Okay, the square root, 331. We got 349 meters per second. Okay. Okay. So at a higher temperature, the speed of sound actually goes up. Okay. Therefore, now I can calculate the wavelength of the low frequency sound, right? I plug in my speed of sound here. The frequency, right? This units of hertz, right, is actually the same thing as 1/seconds. So this actually have units of 1/seconds. So the 1/seconds actually cancel out them both. So the wavelength of the low frequency sound divided by 20 is actually 17.45 meters, right? So if you're making 20 hertz sound, I don't think I can say, this rumbling sound, okay? The wavelengths are actually quite long, right? 17 meters. If you're making very high pitch sound, which I cannot do either, right? The wavelengths of that will be 20,000 in the bottom instead, right? So 349 divided by 20,000, right? This is actually has a wavelength of 0.1745 meter, okay? Or another word, about 17, this is 1.7 centimeter, okay? Okay, so that's the wavelength of sound that are at high frequency, okay? Okay, for human hearing. Okay. Actually, typically, can I do one more example? Okay. So typically, like a male voice will have a frequency of about 350 hertz. A female voice will have a frequency of about 450 because the change in vocal cord when we're go through puberty. So let's say if I want to calculate the wavelength of the sound that I'm producing, so wavelength of sound from Dr. Chu, right? So I use my frequency instead, okay, on average. So let's say my average frequencies I'm producing is 350 hertz, right? So the wavelength I actually produce is about 1 meter, okay? This is why when you have a door that's propped open, I think people in the hallway can hear me because my wavelength actually can get through that door because the width of it is about 1 meter. But if you mostly close it until maybe the gap is like 10 centimeter long, right? You can actually not hear someone in the hallway because the waves actually cannot travel through because the wavelength of the sound is actually much bigger than the gap that is trying to travel through. That makes sense? So that's why closing the door partially actually helps with sound. Okay, any questions before we have Ethan pass out the worksheet?